Hi, you probably see me, but you can hear me.
Yes, I can see. I'm just going to pretend that you're like an alien who has, you know, intrinsic luminosity and.
That's me. That is certainly me.
You're in some kind of glowy hyperspace.
Yes, this is good. So, hi, this is Jonathan. Jonathan McDowell. He's an astrophysicist, and he's probably more capable of telling you what he does than I am. So, take it away, Jonathan.
Yeah. So I have a couple lives really. So in my professional career, I work on a space telescope called the Chandra X-ray Observatory, which is sort of like the Hubble. Except that instead of seeing an ordinary light, it sees X-rays, where it can discover black holes and study exploding stars and so forth. And so I'm on the team here based at Harvard, working for the Smithsonian Institution on this NASA project to hunt for black holes. And then my other life is as a historian of the space program, where I have the website that maintains the list of all the satellites in Sputnik. And so I go on media and pontificate about what the latest rocket explosion or exciting comet landing really means. So that's who I am, and it's good to meet you all.
So basically, we thought that I have some questions, but I have access to Jonathan basically all the time because, well, he gave me his email, so I abuse it. And, you know, that's his problem.
You and the rest of the world. So.
Yes, exactly. So if anyone has anything they've always wanted to ask an astrophysicist.
Yeah, basically anything about space, anything above the atmosphere. Yeah.
Yes. Anyone?
So how are you hunting for black holes? What are you looking for?
Can you hear that?
I couldn't quite hear the questions. Could you say it again, please?
So the question was, how do you hunt for black holes?
Oh, right. How do I hunt for black holes? Well, so here's the thing. I mean, black holes are like famously black, hard to see. But if they're in an environment where they're swallowing lots of stuff, not all the matter. Like if a star gets close to a black hole, or if gas cloud gets close to a black hole, the black hole's a small target, and stuff that's in the black hole's gravity still has some trouble getting to the black hole to fall down it, and so it all piles up. There's a queue for the material to fall in. As that material settles through the gravity of the black hole, I have to wave my hands, so I have to get further from the camera. The friction of the material that's falling through the gravity of the black hole makes it really hot. It's like you're dropping material from a big height right through this gravity well, and it hits another bit of material and releases a lot of energy because it's fallen through such a big, effective height. And when things get really hot, they put out X-rays, and so they put out a lot of radiation. In fact, it turns out that if you throw stuff at a black hole, if you throw enough stuff at a black hole that it can't swallow it all at once, it can convert up to 40% of the rest mass of that fuel into radiation, into light, by E equals mc squared. And so it's really bright, and you can see it halfway across the universe. And so you can see these things, but in the invisible light, they look just like stars, right? They're a billion times brighter, but they're a billion times further away, and they kind of look just like little stars. But when you look in the X-ray sky, the ordinary stars aren't bright. You don't see them. But the black holes are producing scads of X-rays, enormous amounts of X-rays, and so they stand out. If you take a picture of the sky in X-rays, most of the things you see are these black hole accreting these black holes that are swallowing matter. So we actually recently released a catalog of 100,000 of these things. So that they're actually really easy to spot in the X-ray.
Cool. Anyone else? Jag voin. So what he wants to know is he read a science fiction book that had people going near the a black hole, a big black hole, in the book it was talking about how the experience of time got warped basically because of the black hole, that it felt as if the time was going slower. Is there any actual science behind that, or is that just...
Absolutely. Of course, this was the whole premise of the show Andromeda, if anyone saw that, which is otherwise pretty cheesy. But so that's absolutely what happens, and we see the effects of that in our observations. So what happens is, as you go deep into a gravity field, the time passes slower. In the sense, if you do a close pass of the black hole and come back out again, you're taking a shortcut to the future. The amount of time that you pass through is less than the amount of time than someone who spends their time far away from the black hole. And so this is called the gravitational redshift, and it's it can be quite substantial. And it's not just black holes that do this, right? Anything with gravity does this. The Earth does this. Time on Earth is passing more slowly than time sort of out in the solar system far away from Earth. And so we actually have to mess with the atomic clocks on the GPS satellites to correct for this effect. That the GPS satellites that you use to figure out how to get to your local Starbucks they're 20,000 kilometers above the Earth, which is like nothing. But even at that tiny distance of 20,000 kilometers, we have to actually adjust the rate at which the atomic clocks go to account for the fact that time is running at a different rate that far up in the Earth's gravity field from us poor schlubs down at the bottom of the gravity field on the surface of the Earth. So this is a real effect that actually has engineering consequences even today. And but of course, the thing about black holes is that things that are like 1 part in a million effects on sort of stuff in Earth and near Earth space become like huge effects when you go near the black hole. And so yeah, you go within a few radii of the black hole and you come out again, and many years will have passed in the outside world.
So
and the other thing, actually one more thing I'll say about that is, as you actually go to the event horizon of the black hole, you're basically going infinitely far in the future. So if you're going toward a big black hole, it has to be a big black hole if you're going to survive. You go into the black hole, not only can you not get back out again, but in some sense, even if you could, the entire history of the universe outside has already passed you by, and you're infinitely far in the future. So black holes are not only hugely warped pieces of space-time, but their surfaces are infinitely far in the future.
So is the effect, how noticeable is it? So if you compare the experience of time on Earth versus the experience of time, for example, on Saturn, would there be much of a difference, or does that need to be...
No. So the key thing is the rate at which time, the rate of time shifts is it goes as the ratio of how far you are from the center of the gravity well, of the center of the object, to to what's called the gravitational radius of the object. And for Earth, the gravitational radius of the Earth is 4 millimeters. That's how big the Earth would be if it turned into a black hole. And so, to the extent that we're a lot more than 4 millimeters from the center of the Earth, it's a very, very tiny effect, right? And similarly for Saturn and even for the Sun is the grav radius of the Sun is about a kilometer. Well, the actual Sun's 1,000,000 kilometers across. So if you're at the surface of the Sun, time is running 1 part in a million slow, or compared to the outside universe. So in the solar system, things are like at the 1 part in a million level. You don't really notice the difference. And that's why, you know, it only really becomes noticeable if you have something extreme like a black hole, where you can get really close to the gravitational radius.
Right. Cool. He wants to thank you. Anyone else? Anyone? Oh, okay, we'll go to my questions then. So what is the most exciting thing that's happening in space today?
Well, you know, I think, and you're talking about space as in humans exploring space.
Either or.
Yeah.
Both. Fine.
Or just astrophysics discoveries.
Yes.
I mean, I think, you know, so I just spent a week at the 15 Years of Chandra conference. Chandra is our X-ray telescope. We've been in space for 15 years, and we had a big meeting where all the X-ray astronomers from all over the world came to say what they've discovered and kind of have a retrospective. And there were some really exciting results. I think the most exciting was my colleague Ezra Bulbul. She's an astronomer of Turkish origin, although she's working here at Harvard. And she's discovered a glow from clusters of galaxies. So stars group together into galaxies, galaxies group together into clusters of galaxies, because gravity likes to clump things. And it turns out that there's these big gas clouds filling clusters of galaxies. And if you look at the X-rays coming from these big hot gas clouds, they're like at millions of degrees, that you see the characteristic radiation that we'll call the spectral lines from, for example, iron atoms in the cloud that get very hot and radiate, hydrogen atoms in the cloud, but we also see a line that we don't recognize, and it's only seen in these big scales. And there's a suspicion that this new line that we've never seen before, this new radiation of a very particular color, is the signature of dark matter at last. That's the hope, that we may be seeing dark matter particles and dark matter antiparticles annihilating and creating radiation on these very big scales. And so if that's right, that's hugely exciting, but it could also be some previously not understood feature of the X-ray camera on our satellite that's kind of, you know, creating this effect. So there was like a lot of discussion, do we believe it, do we not believe it, ooh, maybe it's true, but we don't want to get too far ahead of us, because 9 times out of 10 the exciting discovery turns out to be a mistake. So that's an exciting thing. And the other, a related thing in a sense, is we also been watching a gas cloud with the exciting name of G2 fall near the black hole in the middle of our galaxy. So there's a big black hole in the middle of our galaxy, and we can actually measure its mass, because we actually see, there are movies of like the stars moving around it and orbiting around it. Normally, you know, things in astronomy take millions of years. You know, you come back, you take a picture, 50 years later it looks identical. But near the center of the galaxy, the orbital speeds are so high that in a 10-year period you can see stars whip around the central black hole, which lets you measure its gravity. And we see a gas cloud going close to the center, and we think it's in the process of being ripped apart. And we were expecting the black hole to flare as it swallowed material from the cloud. But so far, to our huge surprise, absolutely nothing happened. Which was sort of disappointing. Like all the satellites, all the telescopes were pointed at this thing. Like, oh, March 2014, it's gonna, something really cool is gonna happen. Yeah, nothing. And other cool things happened just as we were staring at the central black hole, waiting for this to happen. Right next to it, a thing called a magnetar turned on. It's a magnetar is a neutron star, a very dense star that has a very strong magnetic field, and it goes. Sometimes it doesn't shine much, and other times it switches on and is really, really, really bright. So this previously unknown magnetar decided to wake up right next to the galactic center and send out huge amounts of X-rays, which blinded us so we couldn't even see the darn gas cloud anymore because there was so many X-rays coming from this magnetar. And then we see also in the black hole flaring every few days, few weeks, as little. Well, we think what's happening is that asteroids are being torn apart, falling into it. And so we're actually seeing these little X-ray flares. We've seen 60 of them now. And there's a big argument about, well, is it the black hole ripping apart asteroids, or is it something slightly more boring, like plasma that's having gas that's being torn apart by the black hole, and you're seeing what are called magnetic reconnection events, like we get in the aurora here on Earth. So I think finally we're starting to actually see direct effects of things happening near the black hole in the center of our own galaxy. So that, I think, is pretty cool.
Cool. Anyone else have more questions now?
And then, of course,
No?
there's the comet landing, which is pretty cool as well.
This is what I was going to come to next, because I wanted to ask you, since there have been private companies going into space and working hard to get into space recently, but there have been these accidents and such that have historically, for example, Columbia crash caused a huge drop off in the enthusiasm about going to space. Where do you think these accidents are? How do you think they're going to affect, or if they are?
I don't think they're going to have a big effect, actually. I mean, but I think you have to distinguish the two accidents. And for those who don't know, let me just say, so the two accidents were, there was a rocket going to deliver a cargo ship to the space station that blew up just above the launch pad in a really spectacular display of fireworks. And then there was the tragic crash of, or in fact, in-flight disintegration of the Spaceship Two rocket plane, in which one of the two pilots was killed. And I think that the Spaceship Two crash is the more significant one, in that industry is not established, that there were a lot of doubts already about the particular design that they're using. And so the fact that and the investors are already pretty pissed that the thing is like 5 years behind schedule, and so there's a big danger that the investors will pull out of this Virgin Galactic project to have and for those who don't know, the idea is that you give them $200,000 or so, and you get a 15-minute ride into space on a suborbital ride. And I think, in principle, this is something which there could be a market for if it's safe. But if people are worried that for their $200,000 they just get fried, that's not going to sell so well. And so, the good news for Virgin Galactic is it seems like this accident was a screw-up on the part of the pilot. And they haven't released the official accident report yet, but it's pretty clear that the guy pulled the lever that was marked, "Do not pull this lever below Mach 1.4." And they were going through the sound barrier at Mach 1, and he pulled the lever, and he went, "Oh crap, I shouldn't have done that," and he tried to switch the engine off, but he wasn't in time. And what happens is the lever releases, the rotating tail of the spacecraft, and it doesn't deploy it, but it unlocks the bolts. And then what happened was that the rotating tail rotated, which it wasn't meant to do at that speed. And probably what happened was, even though they didn't command the rotation, having unlocked it, the vibration of going through the sound barrier was enough to make it spring open, and then it just tore the rocket plane apart. And luckily, one of the pilots was torn free, and his parachute opened automatically, and he regained consciousness on the way down. But the guy who pulled the wrong lever did not survive the crash. So that's all very sad. But it means that the basic concept of the spaceplane is maybe not compromised. The rocket engine worked okay, maybe, and so I think that they'll fix that. They'll go on, and it's just a matter of whether the other concerns that people have about this project will not be resolved for a while now till they build the replacement ship. The cargo ship to the space station is another matter, because there's a lot of confusion. What's new about commercial stuff on the space station is that the cargo ship itself is owned by a commercial company, and NASA's basically just paying for the pizza delivery. They're paying for, give me, here we have some cargo we want on the space station, get it to us. But the rocket, which is the thing that went wrong, the fact that the rocket is commercial, that's nothing new. NASA hasn't been launching rockets since the 90s. Almost all rocket launches in the United States and Europe have been commercial for 20 years, and they've had rockets blow up before. So I really don't think that the exploding Antares rocket is going to have a long-term effect on the on the space station program or anything like that, on commercialization of space. What it will do is that no one's ever going to use 40-year-old Russian rocket engines that have been sitting in a plastic bag in the Soviet Union for 30 years. This rocket that blew up, they used these refurbished engines from the Russian moon program that were built in the early 70s, and the Russians canceled their moon program when the US won, and these engines just sat around for 40 years, and then Aerojet bought them and refurbished them and spiffed them up, and that turns out to have been a bad decision, cheap as they were, and so now that company is going to be buying sparkly, brand new, shiny Russian rocket engines instead of 40-year-old Russian rocket engines, and so we'll see how that goes. But it turns out the Russians build better liquid rocket engines than we do. Because they launched a lot of missiles during the Cold War.
Cool. Just a second. Okay, I was just checking. We have a quiz that people have been filling out, and we've asked about Rosetta and Philae, and I didn't want to compromise that. So
do I have to take the quiz?
No. You can if you want. There are fabulous prizes. It's in Finnish though.
Yeah, that could be tricky for me.
That could be tricky. So yeah, can you talk about Rosetta and Philae? Philae?
Yeah, Philae, I guess. I mean, it's it's originally a Greek word mangled by European space scientists, so I don't know what the correct pronunciation of the rocket probe is. But yeah, so this is an incredible achievement, and I think it's worth just starting with the fact that it's no longer the U.S. that's doing the most innovative things in deep space, right? That this is a European project. And we've also seen the Japanese do cutting-edge stuff in deep space. The hegemony of NASA in this business is over. Rosetta was going to be launched back in 2002 to a comet called Vertinen, and then an Ariane rocket went bang, and they went, "Oh, we better not do that." And so Rosetta's launch was delayed a couple years, and they missed they missed the train to the comet, so they had to pick a different comet. And so this comet that they're visiting, 67P Churyumov-Gerasimenko, was sort of a backup choice because of the delay. But it's worked out really interestingly. So this comet is it's on an orbit. I forget the orbital period. It's like 10 years or so. It's not a comet that's coming in from the Oort cloud. The classic comet stays out almost in interstellar space, 100,000 astronomical units. That's 100,000 times the distance of the Earth to the Sun, and falls in toward the Sun. It's like an ice ball, and it falls in, and as it gets close to the Sun, it starts evaporating and making this huge long tail, and then it whizzes out again after whizzing around the Sun really fast into the outer darkness. And we'd really like to visit one of those, but they're going super fast, and we can't match speeds with them. So, and also since they only come through once every million years or so, I mean, a given comet takes like, well, maybe 100,000 years to go around the Sun. We can't predict when it's coming. So instead, what happens is occasionally comets pass close to Jupiter, and that changes their orbit, and they get trapped in an orbit that no longer goes back out to the Oort cloud, but gets stuck orbiting the Sun in a much smaller orbit. And Churyumov-Gerasimenko is one of these. And so that Rosetta spent the past 10 years building up speed to get out into the same orbit as this comet. And it did that by making close flybys of the Earth and the Mars, and it did what they call interplanetary billiards. To every time it passed near a planet, it sped up and the planet slowed down a little, and so it finally got enough speed to match speeds with this comet. And over the past few months, it had been approaching the comet, going to orbit around the comet. It's the first probe to orbit a comet, taking amazing pictures. And I think the most amazing pictures from the Rosetta mission, have not been the ones from the lander, but the ones taken from like a 10-kilometer distance by the orbiter. And then so the orbiter has this little lander called Philae, which is about 100 kilograms, and Rosetta threw the lander at the comet. The lander wasn't using propulsion. It wasn't like using thrusters to approach. Rosetta just lobbed it in the right direction at the right speed for the lander to settle onto the comet. And the comet is these what we call a contact binary. It's like two roughly round things that came together at a slow speed and stuck onto each other. And so it landed on one of the lobes of this contact binary and bounced. And there were all of these different mechanisms that were meant to make it not bounce. They had a rocket thruster that was meant to push it into the surface, and they had harpoons that were meant to grab onto the surface, and screws and stuff. None of them worked. Because the surface, partly because the rocket didn't work, partly because the surface of the comet turned out to be much harder than they expected. They were scared it was going to be like a fluffy snow pile that the lander would just sink into, but turns out not so much. And you have this 100-kilogram lander, but its effective weight, the gravity of this tiny comet, is only a gram. And so even though it settled very gently, it bounced back up about a kilometer high. It settled back down. So you've got to imagine it's sort of like a piece of paper that sort of bounces and floats and comes back down. And 2 hours later, it settled back down again. And unfortunately, they picked out this perfect landing site, and it bounced from this perfect landing site into a really crappy spot in the shadow of a cliff where it isn't getting enough sunlight to power its solar panels. But just before it ran out of electrical power, it managed to send back huge amounts of scientific data that are going to take people months to analyze. And so I think, you know, it's a huge success. It would be better if it was still talking to us, and it may still, as the comet goes around the sun and the illumination changes, the Philae lander may get more electricity, may get more sunlight a few months from now, and wake up and start talking to us again. And the Rosetta orbiter is still in orbit around the comet, and it's got at least a year more in the vicinity of the comet studying it. So there's going to be, you know, so I think it's a huge scientific success, and the fact that it was, you know, had so many problems shows what a challenging thing it is. That how do you land on something where you have no clue what the surface structure is? Right, and you don't even know in advance what the gravity field is like, because you've got this irregular thing, right? And so, you know, the direction that gravity is pointing is sort of changing from place to place, and strength is changing. So it's a really hard thing to do, and I think that the main thing they've taken away from this is now they have a much better idea of how to design the next one.
So how did they go about guesstimating what the surface is?
Well, we had spectra of the composition of comets, so we knew that there were that they're mostly ice. We measured the density. Oops, sorry. So we know that they're very low density objects, and so we thought they were going to be like snow or a mixture of ice and rock, and then you just sort of, you know, make fake comets on the ground, I guess, and test, you know, what will work on them. But it was really partly guesswork, and the main thing that the mission managers say is the way that you land on something that you don't know what it's made of is that you put on board as many different landing mechanisms as you can think of, and hope that one of them works. So, you know, at least the landing legs seem to have worked, and it sort of landed. So you know, they got some things working. The other problem, of course, which the thrusters show up, is that you launched this thing in 2004, and then, you know, you try and use it in 2014, and, you know, you imagine leaving anything else turned off for 10 years and switching it on and see how much of it works. So that's the other challenge, is making stuff that you can have dormant for 10 years and having confidence that it's going to work the day that you need to use it.
Right. I forgot what I was going to say. Anyone else have anything to ask? This is your chance. We have 15 more minutes, then we have to...
It took us 10 years to try that, but do we have anything else undergoing?
Did you hear that?
No, can you say? I heard something about 10 years, but I can't.
Yeah, so it took us 10 years to do that. Is there anything else that's undergoing that's 10 years from now coming to fruition?
Oh, that's a great question, yeah. I have to think about that. I mean, there's plenty of things on the ground. You know, Chandra has now been up, my X-ray telescope's now been in orbit for 15 years, but it was launched in 1999. They started working on it in the 1970s. So space projects, even when, you know, they don't have this 10-year voyage to get to their destination, they still take a long time to get to fruition. I will call out next year, July of next year, there's a probe that was launched in 2000, oh dear, I don't remember, but about over 10 years ago, that is going to Pluto. New Horizons mission, which has been in space for a very long time, heading out into the outer solar system, will finally fly past Pluto in July next year. And it's, you know, in that time, right, Pluto stopped being a planet, and you know, lots of things have happened, but this probe is still boogieing on out there, and it's going to spend like an hour in the Pluto system, whizzing past it at huge speed and doing like the tourist thing of like snap, 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 snap as it goes through, and then it's going to head on out into the asteroid belt, and maybe another 5 or 6 years afterwards, visit the Kuiper belt, which is the outer asteroid belt beyond Pluto. It's going to visit a Kuiper belt object for the first time. So that's kind of a great long-term project that's finally starting to come to fruition. What else is on its way? Let me call out a vehicle that's going to launch in a few weeks in Tanegashima, Japan. The Hayabusa 2 probe is going to be launched by Japan to the asteroid Bennu, and the Hayabusa 1 a few years ago was the first vehicle to bring samples back from an asteroid, but it wasn't completely successful, and it only brought a very small amount of material back. So Hayabusa 2 is going to redo the job with a different asteroid, and bring stuff back. So this is the new frontier in solar system exploration. The first early years of solar system exploration, we sent flyby probes like this Pluto probe that just whiz past their target and have one day of glory in their lives as they go past. Then we launched orbiters, which would map a planet, go into orbit around a planet and stay there, and landers, which will go on the surface, and finally rovers. And the new thing is sample return, actually coming back from these places, which is a lot harder, and bringing back pieces of the solar system to Earth with all of the Andromeda strain possibilities that has, so I think that's the thing to look forward to. Is getting samples of these ancient bodies, these asteroids and comets, which we think have material that sort of hasn't changed much since the early solar system. Bring them back to Earth so we can study them properly, and that's what's coming.
Excellent. Anyone else?
Haluaisin kysyä muutosesta. Miten ne syntyy ja miksi niillä on galakseja?
So she wants to know how black holes are formed, and what was the other one?
Miksi niitä on galakseja?
Why they're in the centers of galaxies.
Right. So let me say there are two flavors of black hole. There are the sort of regular size ones that are formed when big stars die in supernova explosions, and there's lots of them in every galaxy. There's a whole bunch in our galaxy. And then there are the supersized black holes, what we call supermassive black holes, and there we have typically one in each galaxy right at the middle, and they form different ways. So the little black holes are formed. So when you have a big star, so a star is a balance between an H-bomb in the middle, a nuclear fusion reactor, and gravity on the outside trying to crush it. So the H-bomb's trying to blow it apart, gravity's trying to crush it, and you get a perfect balance for, in the case of a large star, only a few million years, until it runs through all the hydrogen fuel. It's burnt all the hydrogen into helium. It gets denser and hotter. It burns all the helium into carbon, nitrogen, and oxygen. It gets denser and hotter. It burns the carbon, nitrogen, and oxygen into iron. Eventually, it runs out of things that it can burn, and so you no longer have the nuclear fusion generation in the middle, and so gravity wins, and the star starts to collapse. And the shock wave of the outer layers of the star falling onto the inner layers sort of reflects back and tears the star apart, but the inner layers just keep on collapsing and they form a black hole. So you get a supernova, but in the middle you get a black hole. And you always get, the way a black hole forms in general, I talked about this gravitational radius, which for a star like the Sun is about 1 kilometer. And the way you make a black hole is if you get the amount of mass of the Sun and squish it into a region that's only a kilometer across, the black hole will form. And so it's just getting enough mass into a small enough volume. And so the supermassive black holes that I study in the centers of galaxies, we think form a different way. We think they formed early in the universe. And we think they formed just, when you have the Big Bang, the universe starts off really smooth and uniform. We think the universe is essentially infinite, and it's got this, as the Big Bang happens, it's not a cloud of gas that is expanding into some empty space. It's a cloud of gas filling an infinite space and getting further, every atom is getting further and further apart from every other atom. And so it's really smooth, but it's not perfectly smooth. There are areas where you have maybe one more atom in this volume compared to the volume on its left. And so say you have 100 atoms here and 101 atoms here, the extra gravity of the extra one atom will mean that this one tugs this one more than the other way around. And so it steals another atom, and now you've got 102 and 99, so it steals more atoms. And so the universe curdles due to gravity. You get areas just from random fluctuations. You get areas with very few atoms and areas with lots of atoms that collapse under their own weight. And depending on how overdense they are, they can make stars, but they can also make black holes. If you have enough matter that's overdense, it'll just collapse straight into a black hole. We think you get these seed black holes around which galaxies form. One of the big, actual unresolved questions in cosmology is which comes first, the chicken or the egg? Now, which comes first, the black hole in the middle of the galaxy or the galaxy with the black hole in the middle? We don't know which forms first, but once you've got it, you've got a little black hole in the middle of a bigger gas cloud that's turning into stars from this gravitational curdling effect, clumping. And what happens is the stars evolve, they lose gas in winds, the gas falls to the bottom of the local gravity well, which is where the black hole is. The black hole eats the gas, it gets bigger, and over cosmic time, you get the stars evolving in orbit around the center of the galaxy, and the black hole sits at the bottom where all the gas falls to and just trumps away and gets bigger and bigger and bigger until you have this supermassive black hole. And we think that's what happens. We see that the bigger the galaxy, the bigger the black hole in the middle, and so there's a feedback between the black hole and the galaxy, because the more stars you have, the more you feed the black hole, but also the more you feed the black hole, it becomes what's called a quasar. It shoots out energy, and it shoots out what are called radio jets that blow the gas away and stop the galaxy forming any more stars. And so there's a complicated interaction between the black hole in the middle and the stars around. That and this feedback idea is a fairly new idea that we're just starting to understand, and we're beginning to learn about the evolution of galaxies and the fact that the black holes in the middle aren't just some extra detail, that they're absolutely critical to determining how the galaxies evolve.
Does that answer your question? Excellent. We have 2 minutes, let's say. So that's of course enough time to talk about the future of Mars habitation. Right? Yes?
The future of colonizing Mars?
Yes.
Yeah. And I've got time, by the way, if you can go on longer. But so here's my statement about that is I think that the reason to have astronauts in space at all is to colonize the solar system. I think if you're just there to do science, you use robots. But we don't just want to do science. We don't just want to learn about the universe. We want to go there. We want to live there. We don't want humanity to be a one-planet species, because bad things can happen to good planets. And so I think it is important as a species that we do colonize the solar system, Mars is one obvious place to set up home. It's going to be a while. We had an interesting talk at MIT a little while back in our local informal space group about the Mars One project, which is the idea that you volunteer to go on one-way trips and establish this Mars colony. And the aerospace engineers have done a study of this and shown how long it's going to take for the people on that to die, which is not very long, because there's all kinds of problems with setting up a colony in space. And I think, to set up a colony that is supplied from Earth is very expensive. So you want to do as much as you possibly can there, right? You want to do what's called ISRU, in situ resource utilization, which is a typical NASA-style acronym for doing it yourself rather than importing things. And if you think about what it takes to be a self-sufficient space colony, and I've been thinking about this a lot lately, it's not just a matter of growing some plants. What happens when one of your circuit boards fail? If you want a space colony that will survive when Earth goes down the tubes, you need to be able to have a semiconductor factory, right? You need to be able to have all of the levels of industry that we have here on Earth, and that's an incredible. I think we have to re-engineer our entire civilization. More portable. So that, for example, you use fewer different materials in making your advanced technology, so that it's easier to bootstrap that technology on a different planet. So I think that there's a lot of interesting work to be done on figuring out how you make a self-sufficient space colony, and that's it's going to take a long time.
Just a second. Kello 5. No siis tossa on puoli tuntia merkattu. Okay. 15 more minutes.
Okay, that sounds good, because we started late.
Yes, this is true. Does anyone want to ask anything? Okay. There are people who have to go. But does anyone want to ask anything?
Is there any natural way that the black holes could be destroyed or cease to exist?
So he asks if there is any natural way that black holes could either be destroyed or cease to exist.
Right. Well, natural or not unnatural. The only way that we know of is to wait a really, really, really long time. There's this phenomenon called Hawking radiation, which is a quantum effect, and there's still a lot of the trouble is we're less confident than we were 10 years ago that we actually understand how black holes work at that level. I'm pretty confident that the sort of basic story about black holes is right and isn't going to change, but the detailed theory of the quantum effects around black holes is being really argued about right now. Having said that, the story that we've had for several decades is that although stuff can't get out of a black hole for the most part, if you have particle-antiparticle pairs that form right at the horizon of the black hole, half of the pair can escape, and it's sort of like a temperature of the black hole. The black hole's glowing very slightly. In any normal astrophysics situation, it's swallowing more than it's glowing. But if you isolate a black hole, if you leave it for 10 to the power 60 years, that's to say 1 with 60 zeros after it years, it will evaporate. And the rate at which it evaporates gets faster and faster the smaller it gets. So when I say evaporate, it gets smaller over an unimaginably long period of time, and then in the last 5 minutes, when it gets down to the mass of a mountain, it goes in a blast of gamma rays that will like wipe out anything nearby. And so yes, if you wait a time that is 10 to the 50 times longer than the current age of the universe, you might see some black holes start to disappear. But until then, we're stuck with them. Anything you do to a black hole only makes it bigger. If you smash two black holes together, this is one of Stephen Hawking's laws of black hole thermodynamics. If you smash two black holes together and wait, what you get is one black hole whose surface area is bigger than the surface area of the two black holes you started with. So there's no way that you can. The only way you can end up with fewer black holes is to make fewer bigger black holes by combining the black holes.
So is that the surface area is bigger than the two black holes, either of the two black holes or the two black holes combined?
The two black holes combined. So if you add the surface area of black hole 1 and black hole 2, you get a lower bound. You get the minimum surface area you can get for the combined black hole. And it's for those who are familiar with thermodynamics, the surface area of the black hole is proportional to its entropy. And the second law of thermodynamics says that entropy, the total entropy of the universe, always increases. The second law of black hole thermodynamics says the total surface area of all the black holes in the universe always increases.
Cool. Cool. You have a planet named after you. It was planet
4589. Yes, 4589. It's a minor planet. It's only like a mile across. It's what you'd call an asteroid. And it's in the asteroid belt between Mars and Jupiter. I'm very honored to have it named after me. Basically, I sucked up to the people who calculate the orbits of the asteroids, and so I've always had an interest in asteroids, and I've been working with colleagues on figuring out how to mine them, how to get resources from them, and I'm kind of trying to persuade the International Astronomical Union that if it's named after me, I should have the mining rights for it.
Nice. That would be good. If you could
Makes
ever.
sense, right? It's got my name on it. It must be mine. Unfortunately, it doesn't work that way.
I agree completely, but I think the problem may be actually mining it in your lifetime.
Well, I don't know. I mean, so there are several companies now that are trying to develop asteroid mining technology, and we have a mission called OSIRIS-REx that's a NASA mission that's about to launch in, I think, 2016. And it's going to go to an asteroid and drill into it. And I think it's meant to return a sample, just a tiny one, so not, very useful mining. But it's sort of beginning the development of the technology to mine asteroids. And NASA's talking about sending astronauts to land on asteroids and maybe bring a mini asteroid back to Earth, and I think that's a really good idea. Not because there's any particularly great science that the astronauts can do there, but because it's the next logical step for human space exploration. The great thing about asteroids is you don't need a separate lander. You can just sort of rendezvous with it and step out onto it. So the limitation that the American space program has right now is we're developing this new spaceship called the Orion, which can support astronauts going from one planet to another, but it doesn't have an attached lander that can actually land on the planet because it's too expensive to develop two spaceships at once. So we can't even start the lander development for probably another 10 years. So for now, we've got this spaceship, and we should send it somewhere. And if you send it to an asteroid, you don't need the lander. So So I think that that's an exciting prospect for the sort of 10-year horizon for human space exploration.
Cool. We have one more question over here. Okay. Basically, he wants to know about the lifespan of the sun and how long it will take for it to die. It doesn't become a black hole, does it?
Correct. It doesn't. It becomes a white dwarf star. So the sun is in what's called its main sequence. It's burning hydrogen. It's a hydrogen fusion reactor, and it's about halfway through that phase. It's about 5 billion years, 5,000 million years old, and it's got about another 5,000 million years to go. And at the end of that, it won't have any more hydrogen left in the core, and so it will readjust itself. It will start to collapse under gravity because the hydrogen isn't producing any more radiation to sort of try and push the star apart. And so it will get hotter and denser in the middle as it tries to collapse to a black hole. But what will happen is that instead it will get so hot that the helium, which are the ashes from burning the hydrogen, will itself ignite and start nuclear fusion and stop the collapse and make it glow again. But it will be a different kind of star at that point. It will have a very dense, very hot core that's burning helium, and because of the technical details of how star atmospheres work, the outer part of the star will sort of inflate and become very much bigger and cooler, and it will be what's known as a red giant star. And then it will continue burning for a much shorter period of time, like say maybe a million years, or even less actually, until it uses up all the helium, and it will start burning heavier elements until it ends up with iron, which is so the other, when you burn hydrogen, helium, and carbon and so on, those are, I can never remember exothermic or endothermic. They're the reactions that make energy, whereas when you burn iron, it uses up energy, so you don't get any more useful stuff out of it. And you end up with basically a star that's made of iron with a hydrogen atmosphere. And it stops there because the gravity of the sun is not enough to squish the iron atoms into making it a neutron star. If the sun were bigger, the strength of its gravity would be enough to collapse the individual atoms into one huge, big, 10-mile across atomic nucleus. And if it were even bigger than that, the gravity would be enough to overcome the strong nuclear force that is keeping the protons and neutrons from squishing into a quark soup, and it would squish it even more and overcome the nuclear force, and then it would collapse into a black hole. So it's just about a question of the various sources of pressure, of stiffness, that resist gravity. One by one, as you increase the mass of the star, those are overcome until you run out of things to push back and gravity wins and you get a black hole. And so the sun is just not massive enough to do that. So it'll be a dead lump of iron. But we won't worry about that, because during the red giant phase, the outer atmosphere gets so big that the Earth will be inside the sun, which will not be good for the Earth. So
the red giant phase?
I'm sorry, say again?
How long until the red giant?
About another 5 billion years.
Okay.
So,
that's good.
your long-term real estate investments, you may the real estate values are going to plummet about 5 billion years from now around here. But even before then, what's going to happen is that ever so slowly the brightness of the sun will change, and I don't remember whether it goes up or down now. I'm blanking, but change to the point where if we don't do anything, yeah, I think it will get brighter actually, and so you think we've got bad global warming now. Earth will become uninhabitable over the next million years or so, unless we get our act together and move Earth further from the sun to keep it at a nice toasty temperature. So I think that's our real long-term space program is within the next million years, move the entire planet Earth to a safer position.
Just a small thing. Slight little project.
Yeah. We got some time.
You can do it. She said, "You can do it."
Well, you know, I think that's the next generation's challenge. So you folks can do it.
So anyway, this has been lovely. We are completely out of time because we'll be kicked out of this venue in 45 minutes, and there are things that need to be accomplished. So thank you again, Jonathan, for joining us and
thank you for
answering
inviting
our
me.
questions.
Have a great celebration.
Thank you. And to our guests viewing, thank you for watching. We will be back.